That's good. Okay, so tell me what if we put a 2 in for n. You're Nesta, you're the man. This is great. What would we end up with there?
It's gonna be 1/4 minus 1.
Okay, so it'll be 1/4 minus 1. And then
over 1/4.
Okay. Is that looking like what you want?
No.
So what modification, what tells you it's not what you want, and what modification might you make to your generalization? You're doing so good. Keep going.
So here we can see that like 1/4 is already less than 1.
So what's that going to do to the numerator?
That's gonna make the numerator even like less than 1. It's gonna be less than 1.
Great. So it'll be something less than 1, which isn't something you were really looking for. So what might we change? What do you want to change in the generalization that you proposed?
So it's gonna be 1/2 exponent and no.
1/2.
So 1/2 exponent.
So it's gonna be 1/2 exponent n.
Exponent
n. It's gonna be 1/4. And we add to the only the numerator plus the denominator, like 1 plus 2 plus n. Right.
So can you hold a number? What is your anticipated result when you let n be equal to 2? What is your anticipated result here?
3/4.
Say it again.
3/4.
All right, so that's your intended result, right? The 3/4. Now, how will you use that answer to derive whatever pattern you want to represent to satisfy that condition? How will you translate this 3/4 in a way that makes sense to represent your pattern?
So it's gonna be 1 plus n/2 exponent n.
So you said 1 plus
n/2 exponent n.
Over 2 exponent n.
No, it's not gonna work.
Why it's not gonna work?
Because if I say 1 plus n, it's gonna be 3 exponent. Yeah, it's gonna be 3/4. No, not 3/4. It's gonna be 8/4.
So how will you modify your first proposal? What were you thinking right now?
I'm thinking that it could be 1 plus 2 exponent 2 exponent 1 plus 2. Nah, it's not gonna work.
You said 1 plus 2?
Yes, but it's not gonna work.
it'll work for this one case, right?
Yes.
But will it work for the other cases?
No.
Not yet. Not yet. So how did you? So I'm going to restate the way you described pattern Z. So you said that the denominator is 1 greater than the numerator. What's another way we could say that to help us here with your generalization? Instead of saying that it's 1 greater than the numerator, how could we restate those so that could help us here?
We can say the difference between the two of them is 1.
Okay, good. So could we?
So difference is 1, right?
So you have in your last generalization something in the denominator. Do you like that? Do you like that 2 to the n in the denominator?
Yes.
Okay, great. Let's hold on to that. So now think about what you just said and how that applies to the numerator, the thing we're going to put on top. So Ernesto, if you could get us another fraction with just the fraction bar with 2 to the n in the denominator, even under the bottom there. There we go. Great. So using what you said to generalize the numerator, what would we do?
We would do 2 exponent n minus 1.
Yes. Well done. All right, now think about now look back what you did up there. Your first time, the 1/2 to the n minus 1, 1/2 to the n. You were so close. What was just the one shift of that you needed to make there?
I just needed to take only the denominator, 2 exponent n minus 1.
Great.
Excellent.
Well done. Way to work through that. So we'll thank you, Ernesto. Go team.
Yes, I want to insert here your extension problem that you proposed. You're thinking about the 1/3. How about if you
Can we go to the asymptote real quick and then go to the 1/3?
Sure.
Okay.
So
So you
share
talked
your screen, Abdul, or you good?
Yes.
I'm sorry, Nathan.
That's all right. Yeah. So you talked about in your paper there being an asymptote. And actually, Ernesto, if you still have the first slide where he was talking about, I guess Abdu, if you have your paper, that would work too, with your table. How do we know there will be an asymptote in this problem? What were the clues that told you that?
Oh, so if I go back to the table with the fractions, here I could see that the numerator is always gonna be less than the numerator no matter what. Because after each move, the denominator, the difference between the two of them is always 1. Always the clue I got.
And so what is an asymptote? What does it mean mathematically here that you're saying it's always going to not be quite?
So an asymptote, or we could say that an asymptote is like a curve that gradually gets closer to a given point, but it never touches it.
All right, so it's constant. It's always approaching, but never touching.
Yes.
Okay. And here you were saying that the fractions here are, you kept saying that that's with the numerator is 1 less than the denominator, and so what does that pattern mean then?
The pattern means that we will never, like, it will never be 1, because the numerator and the denominator always have to be the same thing so that we can get 1.
Got it. Okay, so all right, got it. So if we were to, so now put that back in the problem real quick. If we got it to 1, what would that mean?
if we got it to one, that means we reach the door.
Okay. And so now because the numerator is not gonna be the same as the denominator, what did that mean in the problem then?
That means because the numerator is not gonna be the same as the denominator, that means that in the problem we will never reach the door.
Cool. Got it. Thank you for putting those pieces there. Go ahead, Ernesto. Fire away with that next one.
Yeah, just to build on what you just said. Now that you're thinking about the asymptote in the exponential form, can I ask you, and I want you to think about this, could a linear function have an asymptote?
Linear function. No, a linear function cannot have an asymptote
Why?
because the distance like is always getting added to. Example, let's just say that's 100. After the first move, we say that's like 2. After the second one, 4. After the third one, oh, after the third one, 6. It keeps adding to it. Maybe it's gonna take long, but it's still gonna touch it. It's still gonna reach it.
All right,
So then,
yeah, go ahead.
so what is it about linearity then that makes you say you would reach the door, there would be no asymptote?
Oh, so the problem about linearity is that with linearity, it's like we're doing an addition. We're always adding the same number, like we always keep adding the same number to it. But with the fraction, it's not always gonna be the same thing because we're taking one half of this thing, then after that one half of another different number to add it to that.
So can you give me an example, kind of like what you did with the 100 meters? So what would be an example of a linear moving towards the door that would confirm what you're saying?
So let's just say the distance between me and the door is 10 centimeters, and it
Okay.
says after each move you have to walk 2 centimeters. So after the first move, it's gonna be 2 centimeters. After the second one, it's gonna be 4. After the third one, it's gonna be 6. After the fourth one, it's gonna be 8. And after the fifth one, it's gonna be 10. So that means we reach the door.
Got it. So go to your graph, to your 1/3 table though. And what do you see happening with the asymptote in this table? So in the 1/2, there was an asymptote, you said things were going to approach 1. And in the I really like this extension problem you posed to yourself. And, it's really one of the essential elements of mathematics that we are asking questions of ourselves, even within the midst of the problems we're working on. And so I loved seeing this in your paper. So what do you see column Z approaching? What would that asymptote be for the 1/3 table? Or is there one?
It's not gonna reach 1. The asymptote is gonna be approaching is gonna be 0.5.
Okay, how do you know that?
Because here we can see a pattern. The pattern is that the denominator is always 2 times greater than the numerator plus 1. Like it's like
Aha,
2 plus 1.
great. So you're saying, I'm just going to say what you said using an example from your table here. So we'll just use row 4. So you're saying it's 40 times 2 plus 1 gives me the denominator,
Yes.
right? That would be 81. Did I do that correctly, Abdu, based on what you were describing?
Yes.
Okay. And so you're saying the 1/3 is approaching a half. Do you think that there might be a pattern there? What if we changed it from 1/3 the distance to the door? What if it was 1/4 the distance to the door every move? What do you think that might be approaching? What asymptote might that be?
So for 1/4,
Yeah.
be 1/4, 1/4 plus
I love how you're narrating your work. I appreciate that.
Thank you. It's gonna be 5 over 16. It's gonna the numerator, the denominator is gonna be 3 times greater than the numerator plus 1.
And so that means that if I use 1/4, that the asymptote, we will be approaching what?
We'll be approaching point 25.
If it's 1/4 every time, and you said the numerator was, or the denominator was 3 times plus 1 of the equal the denominator.
Yes.
So it would be approaching.
0.33.
Aha! Why'd you change your answer?
Because 0.25 is like 4 times smaller than 1. But 0.33 is for 3 times smaller than 1.
Oh, so what's the connection? What's the pattern you're building off there to come to your answer? What are you seeing there?
So the pattern I see here is how much that number, how much greater